So, any questions on what we have covered in the last class? Again, just to give a quick recap of what we have done in the last class, we concluded our discussion on K-maps, the technique, okay, and we wanted to then move forward with applications where we can apply them in the design of actual systems, actual combinational circuits, the simplified functions that correspond to combinational circuits. Okay. Now, I have been repeating this again and again, but again, I just want to stress again the process flow, if you will, of how to approach a problem statement. Okay. From now on, even in your assignments, you will see that uh, you will be given a problem to solve. You'll be given a system to design based on certain conditions. Okay. So the approach that you're going to take in the design of such a system is you want to first lay down the level 0 block diagram. That's the first step that you will do in the design of the systems. Okay. Now, what is the level 0 block diagram? Again, it just shows you what are the inputs to the system. So first of all, you have to identify what the inputs are, what the outputs are, and have a basic understanding of what the system should be doing. Okay, so that's your level zero diagram of your system, and I have repeated that many times because if you are able to do this, if you are able to follow this approach, then it will be a much more smoother design process for you. Okay, you can put everything in perspective. You know what the system has to do, because once you have this done, the next step is you put that information down in the form of a truth table, and then followed by that, the rest of the steps are pretty straightforward. Get the K-map, and then you get the function, and there you go. You have designed your system. But this is the critical aspect in the design. Okay, this is the critical aspect. If you're able to do that confidently and through that step, then you're more than halfway through the problem. I would say even more than 80% of the problem is already done. Okay. All right. In the last class, we took the example as our first example in application. We took the example of the design of these code converters. Again, these code converters come in different forms. We looked at one particular example of the design of an XS3 code converter. Again, what's the purpose of this? This makes the hardware implementation more simpler. Just like when you're trying to do the subtractions using binary numbers, right? When you're trying to do the subtractions in binary numbers, taking the ones complement is as simple as inverting the bits of a binary number, right? You take a binary number, given a binary number, if I want to ask you what is the ones complement of that binary number, all I have to do is just invert the bits, and whatever number I get is the ones complement of the corresponding given number. Okay, and then if I want to make it into a twos complement, all I have to do is just add 1 to that, and that makes it into a twos complement. Okay. Now, oftentimes when you're trying to design computational devices, for example, your calculators, you're not really working in binary, right? You don't punch binary numbers into your calculator. You're working with decimal numbers, right? And one convenient way of representing decimal numbers, again, at the end of the day, whatever your interface is, under your interface, you have the actual system, and that system is digital. That system is basically binary in nature. It can only understand ones and zeros, right? So even all the decimal calculations that I want to perform, these have to be within my device itself. These have to be converted to binary numbers or binary codes, if you will, and perform the operations. And then it has to give me the answer in a format that I'm familiar with. Like, for example, whenever I'm trying to do decimal digits, right, or decimal computations, right, my interface should be familiar to me. That means my keyboard should be basically containing numbers, decimal numbers, right? And when I punch my numbers, and then the device basically works in the binary, and then the operation is done, the answer that I expect should also be in the decimal format, right? So when it comes time to view the answer should be shown uh, in a decimal format that I'm comfortable with. So these are the things that we need to understand. So you have an interface, you have an input interface, that's your keyboard that you're basically interacting with, and then you have your system that is interfaced with your keyboard. Your system is all binary, right? We already know that it basically works in binary. So everything that you input, somehow that is being encoded or coded into a binary format. Okay, whether it's symbols, whether it's decimal numbers, whether it's whatever it is. Okay, pictures, everything is binary. And then you have another interface here, or I would say another. This would be your output interface. Again, that should be, providing you information in the format that you desire to see. Okay. So for a calculator, my numbers are all decimal numbers, and then my display, I should be seeing them as decimal numbers. Okay. Now, obviously, everything is happening in binary here. So there should be something here that that is able to decode and encode these numbers. So here, I have my answers as binary. I have to decode them and represent them as uh, decimal answers. Here I have something, again, I have something here that connects, that stays between the input interface and the system, which converts my keyboard entries to binary format. When I'm working with decimal numbers, I'm working with binary coded decimal format, right? Something that we have discussed in the last class. So how do I convert a number, a given decimal number, to a binary coded decimal format? All I have to do is I take each digit of my decimal number, convert that into a 4-bit binary code. Okay, and that basically gives you the corresponding binary coded decimal number. Now I want to stress again that there is a difference between a binary coded decimal format and a binary format. Converting a decimal number into the binary format requires the successive division that we have seen in the previous classes. Converting a decimal number into a binary coded decimal format requires each digit to be converted into the corresponding 4-bit binary code, 4 bits, because the largest digit that I can work with is 9, and I need at least 4 bits to represent 9. Okay, so that's the idea that we have seen in the last class. Okay, now with the XS3 code, what I'm really trying to do is, just like how I do the computations with binary numbers, where converting a given binary number into its one's complement involves, taking every individual bit and inverting it. Can I come up with a similar way for converting a decimal digit into its corresponding nines complement? Okay, because if I can do that, then my computations, my subtractions will be much more faster. All right, so let's do that. So now the way this XS3 code converter essentially, so now I know what my system should be. So this is my level 0 diagram I'm drawing. That's my level 0. Now when I say level 0, you have multiple levels, okay? But I start with level 0. Typically in the design process, I start with level 0, okay? In this case, I have identified what my inputs are. My inputs are going to be individual decimal digits applied as a binary coded decimal value. Okay, so if I'm working with a 4-digit number, I would have 4 of these. Okay, each digit is because each digit, a single digit, would be represented as a 4-bit binary code. 4-bit binary code. So if I want to work with 4-digit numbers, I need 4 of these. Okay. So let's look at 1 digit for now. Okay, and the good thing about the design of digital systems, as you will see, is that it's very modular. If I design 1 for 1 digit, And if I want to make it into multi-digit system, all I have to do is just copy and paste the design, and that's it. So that will make it that you can expand the functionality of your system that way, just copying and pasting it. So that makes it much more simple. All right. So what are the inputs to this? So that's my XS3 code, XS3 code converter I'm trying to design. What are the inputs to this? The input that is being applied is a decimal digit. Of course, I'm not applying as a decimal digit. My decimal digit is encoded as a 4-bit binary code, right? So a single decimal digit is encoded as a 4-bit binary code. So that's my 4-bit binary code. Okay. And then the output would be, as I mentioned before, the way this particular thing works is it takes in this input that is being applied to the system, it adds +3 to it, a binary value of +3, which is 0011, to this 4-bit input, and just spits out the output. So that's the operation itself is pretty simple. And that's my XS3 code coming out of my system. So let's not worry about the decimal digit. Let's start working with the binary coded decimal value here. So here, let me call that B0, B1, B2, B3. That will be E3, E2, E1, E0. Okay. Let me pause here because this is the critical step. This is where most students get confused. So I want to make sure that you got that. You got what the inputs are. Because once we are through this step, you will see that the next steps are pretty self-explanatory. Now, so any questions on that until this point? Do you see how I identified what the inputs are going to the system? Any questions on the input here? John, Connor, everything okay? Does that make sense? Okay, all right. So let's move. Okay, so now that I know what my inputs are, what my outputs are, the input is, again, it's a 4-bit binary code of the decimal. So this is going to be the binary coded decimal value, which consists of 4 bits for a single decimal digit. Now I would translate that information into the truth table. Okay, so let's do that. Now in this truth table, my inputs are B0, B1, B2, B3, which is a binary coded decimal value. My outputs are, I have 4 outputs, E0, E1, E2, E3, corresponding to the XS3 code of the applied binary coded decimal value. Okay, all right. So let me draw the truth table for this. All right. So that's the decimal digit applied. That would be the corresponding binary coded decimal value. It consists of B3, B2, B1, B0. All right. And then that's the XS3 code. XS3 code, which has again 4 outputs, E3, E2, E1, E0. Okay. All right. Now, what is the binary code for a decimal digit 0? The corresponding binary coded decimal value is 0, 0, 0, 0, right? And what is the corresponding XS3 code for the decimal digit 0? Again, the rule is, all it's doing is taking the applied BCD value, adding 3 to that, right? So 0 plus 3 is 3. So the corresponding binary code for 3 is 0011. That's the corresponding XS3 code for 0. And likewise, I will list for everything. So 1 will be 0, 0, 0, 1. Add 3 to that, I would get 0, 1, 0, 0. 2 would be 0, 0, 1, 0. And XS3 code would be 5. 3 would be 0, 0, 1, 1. XS3 code would be 0, 1, 1, 0. 4, 0, 1, 0, 0. Corresponding XS3 code will be 0, 1, 1, 1. 5, 0, 1, 0, 1. Corresponding XS3 code is 8. 6, 0, 1, 1, 0. Corresponding XS3 code is 9, 0, 1, 1, 1. Corresponding XS3 code is 10, 1, 0, 1, 0. 8 is 0, 0. It is 1, 0, 0, 0. And the corresponding XS3 code is 11. 9 is 1, 0, 0, 1. Corresponding XS3 code is 12. And what else? How do I proceed now? I would like to take a pause here. This is where it becomes critical that we understand what my inputs are to the system. What are the constraints that are placed on my inputs? What should I do now? How do I complete this table now? Let me see if I can have any students. Let me see if I can get some opinion from you. Fabian, do you want to think about it? Any ideas? That's very good. Decimal digits, because again, remember that my decimal digits are constrained to be between 0 and 9. I don't have a decimal digit called 10. 10 is still decimal, but it's not a single digit, right? So that's it. I can only apply, my system only takes between 0 and 9 as my inputs. Now what should I do? Because for completing the truth table, I would have 16 entries, right? I only have 9 or 10 entries here. I still have 6 more entries to go. What should I do? What does those entries mean? Okay, Fletcher, you have something? You say, then we open it to sets of 4, 2 sets of 4. That's correct. That's correct. If I'm working with double digits, then I would have to design 2 of those, 2 of these XS3 code converters. Yes. So once I design this particular XS3 code converter, I'm designing for a single digit. For multi-digit, I need multiple versions of those. That's what I said about copying and pasting it. If I'm done with this, if I constructed this design in my software, and if I want to make multiple of these, just copy and paste the design, like you do in B2 Spice, right? When you're working with B2 Spice, and if I want multiple versions of the same circuit, I make one circuit model and copy and paste it. That's called the modular approach, and we will talk about that in more detail in subsequent classes. But anyway, now what should I do for the rest of those combinations, input combinations? What does those input combination mean? So in this case, this is an example where my inputs are constrained to lie between 0 and 9, and the rest of the input combinations are not going to occur. The way my system is designed, the rest of the input combinations are not going to occur. They are precluded from occurring. So what about happens to the outputs for those input combinations? What can you say about the outputs? What should the outputs be? David, can you guess what could be the outputs? For the rest of the outputs, 10 until For the rest of these combinations, 10 to 15, because when I'm trying to draw the truth table, I need to list all possible combinations of my inputs, but my system itself are not going to take those inputs. So because these inputs are never going to occur during the operation, because my decimal digits are basically constrained to lie between 0 and 9, these input combinations are never going to occur, so I don't care about the outputs. So this is my classic example of a don't care situation. I don't care about the outputs in this case, so I basically list them as don't cares. So now I have an opportunity to actually utilize these don't cares for my advantage, right? Okay, so that's good. My truth table is complete. Now it's time to get to my function. Okay, I would like to, so these are my outputs. I would like to view each of these outputs as independent outputs that are independently dependent on these input combinations. Okay. When I say independent, as in these are independent from each other. E0, E1, E2, E3 are independent from each other, and each of my output is a function of the same inputs in different formats, of course. Okay. Now let's look at E0 to start with. E0. What could E0 be? E0 as a function of B0 through B3. What can you say about E0? Of course, you can always draw a truth table for that, which links E0 or which relates E0 to these inputs, and you can get an output. But in this case, the relationship is quite obvious. Just by looking at the truth table, I can directly write what my E0 should be as a function of B0, B1, B2, and B3. What do you think that should be? Any ideas there? My E0, those are my inputs, that's my function, and I can clearly see that my E0 and B0 are somehow related. My E0, exactly right, E0 is B0 prime. That's it. That's how you realize the function. It's only dependent on B0, and that's the relationship. So I got E0 now. I don't have to draw the K-map for that, and probably you'll be getting exactly the same thing. Okay, what about E1? Do you see any kind of relationship for E1? Again, I'm trying to avoid K-maps. I mean, you can do it. It's a foolproof method. But if I can get it directly from the truth table, if I can directly see the logical expression, logical operation, I might as well just do it from the truth table, right? For example, E0 is that, I can directly see the relationship. What about E1? Do you see any relationship, or do I have to take the truth table? So that's 1 0 0 1 1 0 0 1 1 0. Okay. B0 B1 1 0 0 0 is 1 0 1 is 0 1 0 is 0 1 1 is 1, so that's not going to work. Should I do the truth table for this, or do you see any logical expression directly from this table?
The only way I could imagine it would be to. I'm not sure.
Okay. Yeah, it looks like somebody's got that. Somebody said, okay, is it B0 B1 plus B0 B1 B0 prime B1 prime. Could that work? That's correct. Or I can say this as B0 XNOR B1 or B0 XOR B1 prime. And looks like that's working, right? If I just look at B1 B0 and E1, right? Now, if you recall, my XOR or XNOR, let's take the example of XNOR. For an XNOR gate, the output is 1 when both the inputs applied are the same value. Okay, for the XNOR gate. Now 0, 0 gives me a 1. 0, 1, now both the inputs are different values, gives me a 0. 1, 0 gives me a 0. 1, 1, same values, give me a 1. 0, 0, same values, gives me a 1. 0, 1, different values, gives me a 0, and so on. So that works. So in this case, my E1 is simply B0 XNOR B1, which can be expressed in in all the 3 different ways. The same thing expressed in 3 different ways. So that's good. So I got E0, I got E1. All right. What about E2? Let me actually do E2 as a K-map. That's so let me do that. So now I'm drawing a K-map that relates for I'm drawing a K-map for E2, which takes in inputs B3, B2, B1, B3, B2, B1, B0. Okay, now let's put down the values for E2 as a function of B0, B1, B2, and B3. Okay, so I have 0, 1, 1, 1, 1. So that's 0, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0. And then you have 1. And then rest of them are all don't care. So now I have to account for those ones and this one as well. Okay. So in this case, how do I do this? Now, prime implication, I will use my don't cares to my advantage to get a larger combination of adjacent cells. So here's one I can get. Then I have to account for this one. I'll do this using these don't care conditions. And then I have to account for this particular one by, let's do this. Okay. So those are my prime implicants. And I can write E2 as, so in this case, I have B, so going from this cell to this cell, I have B2, and then B1 prime, B0 prime, plus I have 2 more prime implicants. Okay, so for this particular combination of adjacent ones, I get, I have from here, I have B2 prime, and if I go from here to here, I have 0, 1, 1, 1, so I have B0, plus again B2 prime, going from here to here, I have B1. Okay, and that gives me my E2. What about E3? So let's do for E3 as well. Okay, let me see if I can do this here. So that's for E3. Again, my inputs are B3, B2, B1, B0. 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. And for E3, I have 5, 6, 7, 8, 9. Okay. 0, 1, 2, 3, 4, 5, 6, 7. Let's see. Yeah, 5. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then rest of them are all don't cares. Okay. And that's my E3. That's for E3. Okay. Is that correct? 0, 1, 2, 3, 4, 5. From starting with 5, I have ones. 0, 1, 2, 3, 4, 5 is 1. 6, 7, 8, 9. 8, 9. They're all ones. And then rest of them are all don't cares for E3. And now I have to combine them. What is the best way to combine them? So I could combine these two ones into this combination. So that's accounted for. And now I have to combine these two adjacent cells. And that will give me E3. Now I don't need this truth table anymore. I'm going to obtain all the information from the truth table. Now
Professor?
I can just, yes.
So for the bottom row there, like could include the next row up of all the don't cares to get.
Oh, you're right. You know what? You're absolutely right. I can actually use these into a larger combination. That's right. Yeah. Thanks for pointing that mistake. Yeah, that will be the prime implicant in this case because I can use those to my advantage. Okay. So what is my E3 then? So E3 would be, so for this particular combination, my B1 and B0s are all eliminated when I go across. When I go down, only thing that remains is B3. That's B3. Or, and then these two combinations, I have, what do I have? That's B3, go from here to here, that's going to be B0. That's B3, B0. Or, and again, I'm sorry, that's B2, not B3. B2, B0 plus B2, B1. Okay. That's it. So now I have implemented all my inputs, all my outputs as functions of these inputs, and now I can actually draw my circuit, right? So in this case, my E0 is simply B0 prime. Let me do this. That gives me my E0. My E1 is B0 exclusive NOR B1. Okay, that's E1. That's good. And then E2 is a little complicated. Let me see what I can do. B2, B1 prime, B0 prime. Let's see, E3 is fine. Okay, B2, then I have B2 and B3. Okay. So my E2 is going to be B2, B1 prime, B0 prime plus B2 prime, B0. And all of these going into an OR gate to give me my E2. So here I have B2, B1 prime, B0 prime, B2, B1 prime, B0 prime, plus B2 prime, B0, B2 prime, B0, that's B2 prime, B0, plus B2 prime, B1, plus B2 prime, B1, B2 prime, B1, that's B2 prime, B1, and that's my E2, okay? So that's B2, B1 prime, B0 prime, plus B2 prime, B0, plus B2 prime, B1, so that's my E2. And finally my E3, which is B3 plus B2, B0, I have two AND gates, B2, B0, that's B2, and okay, let me just put it B0 here, okay? So that's the same wire that is going there, and B2, B1, okay? Instead of just making it all a big mess, and that's my E1, E3. And that's it. So that's my device. Now we know exactly what should be inside. Started out with the level 0 diagram, and now I know exactly what the innards of this system should look like. Okay, so that's my XS3 code converter. And you can verify. Okay, now let's take the example of 7. Oh, yeah, 7. Let's take the example of, so now we don't need this. We can take that out. Just to give you an idea about how this XS3 code works. So let's take the code 7. Now XS3 code 7 is written as 0111. The corresponding XS3 code for that would be what? Plus 3, which is 10, which is 1010. Okay. And 2, let's say. 2 would be 0010. The corresponding XS3 code for that would be plus 3, which is 5, 10101. Okay. Now, if I give you 7, and I ask you to find what is the ninth complement of 7, what would that be? The ninth complement of 7. You subtract 7 from 9, right? That's how you find the ninth complement of 7. Subtracting 7 from 9, or 10 minus, by the definition, basically it's basically 10 minus 7 minus 1, right? Which is 2. Or you can say this is 9 minus 7, which is 2. All right. Now, the XS3 code for 2 is 0101. The XS3 code for 7 is 1010. Now, do you see the relationship between these? So that's the given number as an example. That's the corresponding XS3 code. How do you get the corresponding nines complement? Once they are present in the XS3 code format, you can see just by inverting the bits, 1010, invert individual bits, just like how we do for the ones complement, that will give me by nines complement, right? 0 becomes 1, 1 becomes 0, 0 becomes 1, 1 becomes 0, and that's the corresponding nines complement of 7. So again, the idea behind this XS3 code format is to finding the nines complement as simply as if you would find the the ones complement just by inverting the individual bits. So that was the idea. I just wanted to demonstrate that. Okay. Now let me pause and let me see if you have any questions about the procedure that we followed. And that is the general procedure we will be following all the time. Okay. Any questions so far? So that was our first example of a design of a combinational circuit given a problem specification. And you've seen the approach I've taken, going from the first step, level 0 diagram, to the truth table, and from the truth table to the K-map approach, and obtaining the simplified function. So now we are basically putting together those Lego blocks. We're learning the technique to put them together in the right format to provide me or to serve the purpose. All right. Now, as the second example, so we have done with this. Now, what if I want to, let's say we have designed, let's say you're designing a calculator, for example. A calculator, a simple calculator that you would punch numbers into it, and then you want to have the display. Right? You want to have some kind of a display that would show you what the result of the operation is. You're trying to design a decimal calculator. That means it's going to take decimal inputs. You have these, so you design your keyboard to contain those decimal inputs. And when I punch them, then you need to have some kind of an interface that would convert those into binary coded decimal formats within the device, right? And you would perform the operations in the binary coded decimal format. And then you would display the answer in the decimal format. So the answer that you're going to get inside the device are going to be in the terms in the form of a binary coded decimal format. Okay. Still binary numbers that we call binary coded decimal format. Okay. But I want to see them as a decimal number, as proper digits, right? Like you see on your computer screens or on your calculators, right? You actually see them as decimal digits. Okay. So obviously we need to have some kind of a decoder in the device that would convert my decimal answer. Okay. Now, as long as it's within the device, so this is your device, it's all binary. As we discussed before, so you implement your design, your digital system design, digital, let me call that actually a decimal adder, let's say, or subtractor, or slash multiplier, and so on. Now, as long as you're operating within the device, this is all in the binary coded decimal format. Again, when I say binary coded decimal format, it's still binary. It looks binary, ones and zeros, right? It's just a format, but it's still all binary numbers. And then what I'm trying to do is I'm trying to obtain my answer as a decimal number. That's my display. I want to view it, whatever the answer I get, which is in the binary coded decimal format, as a decimal answer. Something like this. Right? That's what you see in your calculators. Now, how can I do this? How can I so obviously there has to be some kind of a decoder here to which you apply your binary coded decimal values. Okay, and the decoder basically should be interface to your display. Okay, and that would decode the binary coded decimal value into a decimal digit. That would basically, so yeah, and because it's applied, because it's interfacing the display, we call that the display decoder. Now each decimal digit is decoded from a single binary coded decimal value, right? Each decimal digit. So that means if I have 3 digits to display, I need to have 3 different display decoders, each for one binary coded decimal value. Okay. In this example, let's just work with one. And then again, as I mentioned before, if I want to make more, if I want to display more digits, all I have to do is I will just copy and paste the same design. Okay. So let's if I convert, if I'm able to display a single digit, then the same circuit can be replicated to display multiple digits. Okay. So what we are trying to do now is to design a display decoder that would display my decimal answers as decimal digits. Okay. All right. So let's actually do that design. So here again, I would like to identify. So this is how I'm going to display it. Now, in terms of display itself, it's actually very simple to understand. You must have seen it. You because you operate your calculators all the time. You have these 7 segments, right? To display a single decimal digit, I would have 7 segments. Okay. One, that's the segment 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and 7. So that's the 7 segments. Let me call them A, B, C, D, E, F, and G. Okay. Now you can imagine each segment to be an LED, okay, a light emitting diode. Okay. Now if you want to display, let's say 2, the way I would display that is I would power up A, B, G, E, and D, and then I would not provide the current to the rest of those uh, uh, segments or LEDs, right? So I'm basically lighting up A, B, G, E, T, right? And the rest of them are not powered, so that they appear something like that. That's how I would display 2, number 2, and so on, all the other digits. Okay. Now, so this is what I'm going to design now. I'm going to design a combinational circuit again, which is called a 7-segment display decoder. Okay, I would like to come up with a level 0 diagram for this. What is this supposed to do? It's supposed to take in a binary coded decimal value that could be a result of an operation, right? A single binary coded decimal value, and display that on my 7-segment display, something like that. Okay, now let me ask you, what are the inputs to this? How many inputs do I have going into the system, and how many outputs do I have coming out of the system? So this display, the output, obviously these outputs have to be interfaced with these LEDs, right? I need to determine if I want to display 2, when I apply a binary coded decimal value of 2 here, that means I need to display 2 in this format. It means I need to only light up A, B, G, E, D. So 4 inputs, 7 outputs, perfect. What are those inputs? So I have 4 inputs. That's the right answer. I'm trying to display a decimal digit, right? Binary coded decimal value. Okay. So B0, B1, B2, B3, representing a binary coded decimal value, a single binary coded decimal digit, if you will, expressed, a single decimal digit expressed as a binary coded decimal value. Okay. And then outputs, 7 outputs, as you mentioned, which goes A through B, A through G. Okay. And each of my output, like A is connected to the light segment A, B is going to the segment B, C is going to the segment C, and so on. So if I want to light up A, that means I need to provide a value of 1 on A so that my A is lighted up, right? And likewise, if I want to light up A, B, like the number 2, that means my A has to be a 1, B has to be a 1, C has to be a 0, D has to be a 0, E has to be a 1, F should be a 0, G has to be a 1. Okay. So that's how your outputs are determined. Based on what you apply, that's how you determine your outputs. So now I know that the relationship between the outputs and the inputs, my level 0 diagram is complete. Now it's time for me to translate that information into a truth table, or summarize the working of this device, this decoder, the display decoder, into a truth table. And let's do that. Okay. So now it's actually fun. All right. So now I have, again, that's the decimal digit I'm trying to display. Okay. That's my binary coded decimal value applied. That's the BCD value applied to my input. Again, I have my BCD expressed in four binary bits, B3, B2, B1, and B0. Then my output, I have A through G, A through G, A, B, C, D, E, F, and G, right? So my decimal digit is 0. I'm applying a binary coded decimal value of 0, 0, 0, 0, 0, 0. And what should light up? Let me actually, for reference, let me just do this. That may be easier. A, B, C, D, E, F, and G. Yes, all but G for 0. That's correct. So that will be 1, 1, 1, 1, 1, 1, 0. 1 will be 0, 0, 0, 1. And I would light up B and C in this case to be 1. And likewise, I can fill this table now. 0, 0, 1, 0 is 2. So that's A, B, G, E, and D. A, B, G, E, and D. Rest of them are all zeros. 3 would be A, B, C, D, and G, right? A, B, C, D, and G. 4 F, G, B, C, D. No, F, G, B, C. F, G, B, C. F, G, B, C. 4 is 0, 1, 0, 0. F, B, G, C. Rest of them are all zeros. 5, 0, 1, 0, 1. What is 5? 5 is A, F, G, C, D. A, F, G, C, D. Okay. A, F, G, C, D. 6 is 0, 1, 1, 0. So I'm applying this. I'm going to display 6, which is F, FEDCG, right? FEDCG. Is that correct? Yeah. 7. Sorry, A should be for 6. Okay. Okay, yeah, you're right. Because 6 is displayed as, right? How you display 6? Okay, yeah, that's correct. So A should also appear 1. Okay. 7 is 0, 1, 1, 1. So yeah, without that I would have displayed 6 as B, which is not good. Yeah, you're right. 7 would be A, B, C. That's it. A, B, C. 8 would be all of them. Everything is displayed. 9 would be 1, 0, 0, 1. How do I display 9? A, B, F, A, B, C, D, and G. A, B, C, D, and G. Okay. What about the rest? And F2? F 9. Yes, that's correct. F. Yeah. Now again, should phi have a 1 for F, not E? Phi have a 1 for F, not E. 5 is that. Yes, that's correct. Yes. So 5 is A, F, G, C, D, right? 5 is A, F, G, C, D. Okay, that's correct. Now again, I'm dealing with decimal digits. My inputs are binary coded decimal values. I can only go from 0 to 9 because that's what my decimal digits are. And for the rest of them, okay, should 9 be 0 in D and E? Okay, 9, 9, 9, 9. So 9 is what? 9 is something like that, right?
It can be interchangeable. You can do it with or without the bottom one.
Oh, okay, yeah. Again, it depends on how you want to display it, right? I don't know. Again, when you think about it, uh, how is it displayed in your calculator? Yeah, again, it's optional. I mean, if you want to go like this, that's fine. Then in which case, you don't want to display D. Okay, that's fine. So let's include that then. So D is on. Yeah. So yeah, that depends on how you want to display that, which is up to you. And because these are decimal digits, for the rest of the combinations, because the rest of the combinations are not going to occur, because I'm working with decimal digits for 1, 0, 1, 0 until 1, 1, 1, 1. These are all going to be don't cares for all of those outputs. And that's it. So now I have a truth table. Once the truth table is done, you know, 90% of the problem is done. All you have to do now is the more of the mechanical steps, right? Where you find, where you look at the outputs and try to express the outputs as a simplified functions of B0, B1, B2, and B3. Use the K-map approach and derive the functions. Okay. Now, when you have situations like this, when the number of outputs are more than the number of inputs, when you're dealing with multiple outputs, okay, sometimes it may be a good idea, even though your outputs, each individual output is computed as independent of other outputs as functions of these common inputs. it may be a good idea to see if you can obtain common terms, common product terms between the outputs. Okay. So you should always see if I can obtain common product terms between these outputs. Like can there be any product terms common to F and G implementation or ABC implementation? And I would like to reuse those product terms in my function to obtain my function. Okay, so that way I can reduce the redundancy in my circuit, reduce the power consumption complexity in my circuit. Okay, does it make sense? Now let me see if I can do. Are there any ones that are obvious to compute? No, that's not very obvious. Okay, so let's compute for A and B maybe. So let's take the two tables for let's take the K map for A. That's my again my inputs are B3, B2, B1, B0, B2, B1, B0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. And what do I have? So I have 1, 0, 1, 1, 0, 1, 1, 1, 1, 1. Okay. 1, 0, 1, 1, 0, 1, 1, 1, 1, 1. And then the rest of them are don't cares. Okay. And what do I get for A? So my A would be, if I combine these into a combination of 8 adjacent cells, I can combine these two again into a combination of 8 adjacent cells. I still have to account for this one and this one. Okay, so this one I gotta combine zeros probably. Zeros would have been much simpler. Anyway, that's one, and then I can combine this into the corners. Now here's a classic example where I should have probably combined zeros. Too many number of ones to account for. Okay, and what is my A? My A would be I have this one. From this one, I get a product term B1. From this combination, I get a product term B3. From this inner square, yeah, Monty.
Never mind. Sorry.
From this inner square, I get B2. And then going from here to here, I get B0. And then the corners, I get, going from here to here, I get B2 prime. Going from here to here, I get B0 prime. That's my A. And likewise, I will implement my B, C, D, E, F, and G. And I would like to leave it as an exercise for you guys. Make sure you do that. And what I would like you to see is, do you see any common product terms between all the different functions? So that when you're actually trying to write this up, when you're trying to fabricate one, then you don't have to implement new product terms, right? You can actually reuse them. The more the number of product terms I can reuse, the more simpler I would my circuit would be. Okay. All right. Any questions until this time? Are you with me until this point? So you see how I'm proceeding. Once you are through this step, it's it becomes more more like a you can just coast away with after this step. Okay. All right. Now, that's our second example of application of K-map in the design of a combinational circuit. As a matter of fact, thankfully, you don't have to design these display decoders all the time. If you want to use your LEDs, for example, for displaying some information, you can actually buy these. You can buy those display decoders as a chip, and you can interface them, and then into your circuit, and you can, display the numbers. Okay, so you don't have to construct them yourself by scratch all the time. So these are already available, prefabricated in the form of an IC that you can actually use. Okay. All right. So let's move on. We don't have any other questions. So now uh, let's look at one more example, and then we'll conclude our discussion on the applications. Of course, we'll be applying K-map all through the course. It's not like we're done with this, but this is a good example of how to use K-maps. What kind of K-maps you can encounter, and when I encounter such a K-map, what should I be doing? Okay. So now let's talk about a class of circuits called parity generators or parity encoders, if you will, or I would say parity bit generator. Now, oftentimes, when you're trying to communicate, when you're trying to wirelessly communicate, or it doesn't have to be wireless, when you're trying to communicate through digital communication platforms or channels, okay, the way you do that is, you have a transmitter, and then you have a receiver, okay, and then you have a communication channel between the transmitter and the receiver, all right, and and then you're transmitting information in the form of binary bits through the communication channel. The communication channel could be in the form of, optical cables that go from the transmitter to the receiver. Could be in the form of cables, actually electrical cables that go from the transmitter to the receiver. Okay. Now, oftentimes, when I'm trying to communicate uh, through the channel, you also have noise sources that are acting on the channel. Now, when I say noise sources, what these are trying to do, or what the effect of these noise sources is that some of the times the bits values can change because of the noise sources. Again, when I say bits, what are these really? Right? When I'm trying to use, uh, you know, uh, using optical fibers, then these bits are being communicated in the form of optical pulses, right? And I'm trying to use these using electrical lines. These bits are basically transported as zeros and ones values, the voltage values, right? Now, so the problem is zero corresponds to some level. Let's say the ground level, zero as a ground level. One corresponds to, and in today's times, the difference between those two levels is actually reducing, right? Because the lower the difference, the cost, the energy efficient my system is, right? The power consumption is lower. So one could be at a level of 1.25 volts. So any noise acting on my bit, let's say 0 or 1, my 0 may be changed to a different voltage level, and my receiver may interpret that as a 1. And likewise, my 1 can be changed as a 0, and my receiver at the receiving end may be interpreting that as a 1 or a 0, right? So the effect of noise is basically corruption of your signal. Okay. So oftentimes, what is done in digital communications is that you add these redundant bits, or I would not say redundant, but so you transmit these, transmit information as packets. Let's say if you're working with a simple example, let's say you're working with 4 bits. Okay, that means my each data is packaged in 4 bits, and let's say these 4 bits could represent the pixel value of an image. Let's say trying to download an image, for example. Okay. Now, each of the 4 bits could be a pixel value of an image. Let's say if you're trying to download an MP3, like a sound signal or a MP3 file. Okay. Each of the 4 bits could represent to that to the sample value, right? To the sample level that we discussed before. Okay. So I'm transmitting them as 4 bits. So on my through my communication channel. Okay. And because I need to have some kind of a mechanism at the receiving end of to be able to decipher the signal, to be able to see if there was any instances of corruption while these data bits were transmitted through the communication channel. So I have to have some kind of a mechanism by which this error correction can be performed. Error detection can be performed. That's the first step. I need to be able to detect the error, and also I need to have some kind of mechanism to correct the error. Okay, so let's say some bits have changed because of noise. I should be able to locate the error and correct them so that I get the right information from the transmitter, or the intended information from the transmitter. So oftentimes what is done is, along with these 4 bits, I would transmit what is called some additional bits, and whose sole purpose is to function as error detection and correction bits. So these are codes that are tagged along with my information, error detection correction bits. My data, this is my data. So your data packet now consists of your actual data and also these additional bits that are added that would perform the role of detecting the errors due to noise acting on my signal, as well as correcting those errors. Okay, and there are multiple different algorithms that can be implemented on this. Okay, just if you're curious and if you're interested, one is called the Hamming code, and then you have the Viterbi code decoder. Interesting ways of detecting and correcting the errors. Okay. But now let's take a very simple example of how this detection can be done. At this time, I'm just focusing on the detection of an error. Okay, and you can think about this way. Now, what I can do is, let's say because I'm working with 4 bits, I will define what is called a parity bit. Let's say I'm working with odd parity. Let's say I will define a parity bit such that I would basically generate a parity bit generate a parity bit of 1 if the number of ones in my input stream, in my data stream, the number of ones. So I'm counting the number of ones in my data stream or my data packet. Data is equal to is odd. So a very simple way of doing it, right? So I will look at my data before I transmit it. I look at my data, count the number of ones in my data stream data. The number of ones add up to be an odd value. Okay, I would generate a parity bit of 1. The number of ones turn out to be even. I generate a parity bit of 0. Okay. Now, once I generate them, I would transmit them along with my actual data packet. Okay. So my data packet would consist of now the 4-bit data, and to that I would add as the most significant bit or the least significant bit. Most of the time, it's the most significant bit. I would add them a 5th bit called the parity bit. So in this case, let's say my input is 1 0 0, okay, 1 0 1 1. Okay. A particular input data that I want to transmit is 1 0 1 1. The number of ones in this case is odd, so I would generate a parity bit of 1, and then I would transmit the entire thing over the communication channel. Okay. Now, at the receiving end, what the receiver does is he would basically do this. You look at this received number, so count the number of ones received, and then check that with the parity bit. If those don't tally, that means there has been an error. There has been some error introduced on my data sent, and then either my transmitter has to resend that data, or I have to do something to correct that data. So that's a very simple scheme of error detection through the use of parity bit. Okay. Again, your parity bit can be a odd parity or even parity. Okay. But then you need to have a good communication between your transmitter and receiver. You both of the transmitter and the receiver should be on the same page. Okay. So if the transmitter is sending it as an odd parity, then the receiver should be knowing that it is sending as an odd parity. Okay. All right. So this is what we're going to design in the next class in parity encoder, and followed by that we will actually start looking into the design of actual arithmetic circuits. How can we design circuits that can perform arithmetic operations, additions and subtractions and so on. And with that, we'll be introducing a new technique of designing systems, which is the modular way of doing things. All right, with that, let me stop here, and let me see if you have any questions about anything so far. Okay, so that's a good question. In this scheme, it does not have a mechanism of correcting the error. It's just able to detect the error, but not correct it. But there are other ways, like I mentioned, the Viterbi decoder and Hamming codes. So these are the ones that can actually detect and correct the errors. Okay. But again, that's not the subject of our class. If you are taking an advanced digital signal processing class or signals and systems communication system classes, you'd be able to learn about these techniques. Okay. All right. Yeah. If you don't have any other questions, then let's stop here, and you have a great weekend.